we're looking at reviewing for the final. So going over as much as we can of what we covered for this course. So business calculus, calculus for social sciences. First thing that we looked at in this course were limits. So you should be able to deal with limits both algebraically and graphically. Okay, so let's kind of look at a couple of these, looking at it algebraically. So if we had the limit as x is approaching 25 of x plus 5 in parentheses, all times x raised to the negative 1/2 power. Okay, so when you're looking at limits, the first thing that you want to do is first look and see if you can just go in and evaluate it. So go back in, and wherever you see an x in the function, we're going to go back in and we're going to plug in our 25. Once we plug in our number, we need to drop the limit sign. And so go back in, plugging in 25 wherever we see an x. So I get 25 plus 5, that gives me 30. This 25 to the negative 1/2 power, I know that negative 1/2 power, I can make it positive by bringing that 25 down into the denominator. And so this is the same thing as 25 all over, 25 raised to the 1/2. So here we have 30 all over. Well, something raised to the 1/2 power or a rational exponent, we can rewrite as a radical. And so this is the same thing as the square root of 25. So we have 30 over 5, which equals 6. Okay, so if we can go in when we're taking limits and plug in the number and get some value back like that, then we're good, we're done. There were times though when we got things, what we called were indeterminate. It didn't tell us anything about the limit. And that's where we had to go back and kind of manipulate our function so that we could take the limit of it. So let's say now we have the limit as x is approaching negative 1 of 3x cubed minus 3x squared minus 6x all over x squared plus x. So we're going to do the same thing that we had done before. We're going to see if we can go back in, plug in negative 1 wherever we see an x, and hopefully we get back some number. So we have 3. I'm going to just put parentheses where I'm going to go back in and replace negative 1. So we have 3. I see an x. We're going to cube it. Minus 3. I see an x. I'll put parentheses. Square that parentheses. Minus 6. I see an x. Put parentheses. All over. I see an x, so put parentheses squared, plus I see an x, so put parentheses. So going back and rewriting, putting in negative 1 wherever I had an x and put parentheses. And so here we get, well, negative 1 cubed is negative 1 times the 3 in front, so that's negative 3. Negative 1 quantity squared is positive 1 times the negative 3 in front, so minus 3. Negative 6 times negative 1, so this would be plus 6. All over, so negative 1 quantity squared again is 1 minus 1. So this gives us, if I sum negative 3 minus 3 plus 6, I get 0 over 0. And so this was the indeterminate form. Okay, so that didn't tell us anything. And so this is where we had to go back and we needed to manipulate what we were taking the limit of. And so if you look at it and you get 0 over 0 one way. If they're polynomials and you're dividing, you want to factor, see if it factors. So I noticed that on the top, I can pull out, they all have a greatest common factor of 3x. So factoring out a 3x on top, that would leave us with an x squared minus an x minus 2. In the denominator, I also see that I can factor out an x. So doing that, I get x times the quantity x plus 1. I notice that I can factor a little further because what's inside the parentheses in the numerator is factorable. So there are two numbers that multiply to give us that -2 and add to give us the -1. So that would be -2 and +1. So that parentheses factors as x minus 2, x plus 1. All over x all times x plus 1. So simplify, cancel like factors in the numerator and denominator. So the x plus 1's cancel and the x's cancel. So technically we're left with a limit as x is approaching -1. All we're left with is the x minus, oh, you got that 3 out here, parentheses x minus 2. So go back and do direct substitution. Wherever you see an x, plug in -1. So we have 3 parentheses, -1 minus 2 inside the parentheses, and the order of operations. So we have 3 times -3, which is equal to -9. Okay, maybe one more, limits. So if we're looking at the limit as x is approaching 2 of 1 over x minus 1 over 2 all over x minus 2. Okay, so right away I can see that when I plug in 2 for x, I'm going to get 0 in the numerator and 0 in the denominator. So again, we have an indeterminate form, and so we need to manipulate this. So looking at this, I don't like that I have a complex fraction. So one way is to get rid of those complex fractions. I tend to like to get rid of my complex fractions by multiplying by the LCD of the numerator, or whatever fractions are in the numerator and denominator. There's a couple ways to do it. Basically, we're going to multiply by a fancy way to write 1 to manipulate this. And so my LCD of my two fractions in here is 2x. So if I multiply the numerator by 2x, I want to also multiply the denominator by 2x. So doing that, and the whole point of that was so that the fractions would cancel. I chose something that the denominator divided evenly into. So when I distribute this 2x to the 1 over x, x goes into 2x and leaves me with a 2. Minus, when I distribute the 2x to the 1/2, the 2's cancel and I'm left with an x. All over x minus 2 all times 2x. And so now, when you plug in 2, thing is you still get 0 over 0. But looking at this limit, I notice my numerator, the 2 minus x, is almost identical to the denominator piece x minus 2. They're only off by a -1. So if we pull a -1 out, so factor out a -1, and it could either be the one in the numerator or denominator. I'm going to pull it out of the numerator. So if I pull -1 out of the numerator, this now becomes -2 plus x all over x minus 2 times 2x. Well, commutative property addition, -2 plus x is the same thing as x minus 2. So these two cancel. And now we're looking at the limit of -1 over 2x. So limit as x approaches 2 of -1 divided by 2x. So now when we go back in and we replace wherever we see an x with our 2, we get -1 all over 2 times 2, which was -1/4. Okay, so those were looking at some examples of how to deal with limits, and especially if you got them in the indeterminate form. If for some reason you had radicals in there, I'm not going to do one, but if you had radicals in there and you got the indeterminate form, one way to manipulate that is to multiply both the numerator and denominator by the conjugate. So if you had square root of a plus b, that would be square root of a minus b, changing the sign in between the two terms. So multiply by the conjugate to the numerator denominator, a fancy way to write one. Okay. So now you should be able to look at graphs and be able to look and find limits by looking at the graph. Okay, so I'm gonna give some points while I'm doing this. So we have 1 point of the graph, which is at -2, 0. So x-intercept of -2. And then we have a point that is -1, 3. That's a solid circle, and it kind of looks like this shape. Oops. So we have an open circle at -1, 0. Sorry, not -1, 0. -1, 1. And then we have the graph that has a vertical asymptote on the y-axis. So this is going to shoot upwards. You have an open circle at 0, 3. And then you have an open circle at 1, 1. You have a line that is joining those 2 points I just told you. You have a solid point at 1, 2. And then, I'm sorry, 1, 2, that's in the wrong spot. That open circle below the 1, 2, that, and we're going to have joining the graph to the point 2, 3.5. So straight line joining that open circle with that. And then it's a V shape kind of facing downwards to a point that is at 3, 2. And the arrow shoots down. Okay. So you're given the graph of f of x. And it asks you to look at the graph and find the following limits. So you're looking at the limit as x is approaching -1 on the left of f of x. Okay, so this negative kind of looks like an exponent on that -1 is telling you you're coming in on the left of -1. So you're following the piece of the graph on the left of -1. I don't know if you can see my cursor when I do this. And so as I'm following this piece on the left of -1, I want to see what y value I'm hitting. So I'm getting closer and closer to this y value of 3. And so I can see the limit as x approaches -1 on the left is equal to 3. And then it asks you to find the limit as x approaches -1 on the right. So you had this little plus sign that looks like an exponent. I guess they're called superscripts too of f of x. So on this case, we're looking at the graph, the piece to the right, just to the piece to the right of -1, and seeing what's happening to the graph as we get closer and closer to this x value of -1. What is the y value it's getting closer and closer to? So we saw even if it was an open circle, that is still approaching that value and getting very close to that value. So that limit on the right does exist, and it is equal to the y value of 1. So this would be equal to 1. So part C asks, well, what is then the limit as x approaches -1 of f of x? So if you don't have any superscript on the number of the x value that you're approaching, then you have to look at the left and the right of that value. And in order for that limit to exist, they have to approach the same value. And so we just saw that on the left, we were approaching the y value of 3, and on the right, we were approaching the y value of -1. And so we would say here that the limit does not exist because the limit as x approaches -1 on the left of f of x does not equal the limit as x approaches -1 on the right of f of x. Okay. So D wanted us to find f of -1. So this is basically notation is saying what is your what is your y value when x is -1? So looking at the graph, the x value, the point when x is -1 is right here. And so this is equal to, it's a solid circle there, and so it is equal to 3. It asks what is f of +1. And so looking at this, f of +1 is equal to 2. It's asking you to find the limit as x approaches -1. Okay, sorry, we already did the, it's +1. And with a negative superscript of f of x. Okay, so if we're looking at the graph, so the piece directly to the left of +1, and you're looking at, as we're coming in from the left, the y value that you're coming closer and closer to, even though it's not defined there, it's still equal to 1. So G, what about the limit as x approaches 1 on the right of f of x? So same sort of idea here. If you're looking at the right though of 1 and looking at the graph, as you're getting closer and closer on that graph, following that line, what is your y value as you get closer and closer to x equals 1? And that y value is also 1. So when it asks us in part H, if the limit exists as x approaches 1 of f of x, this is equal to 1. because the limit as x approaches 1 from the left is equal to the limit as x approaches 1 from the right. What if it asked, is f of x continuous? At x equals 1. And so if it's continuous, I would want you to explain why it's continuous. If it's not continuous, I would want you to explain mathematically why it's not continuous using limits. And so in order for a function to be continuous, the limit has to exist. And so we saw from the part above that our limit exists, but that limit also has to equal f of that value. So it's continuous if 1, the limit exists, and the limit as x approaches that value, let's say a of f of x, is the same thing as what f of a is. Okay, so our limit did exist. As we approached 1, we saw that we got back 1. But if we look at f of, what is f of 1? So going back to our graph, when x is 1, we want to see what our y value is. Well, that was part E. We saw that our y value was 2. So when x was 1, y was 2. So f of 1 is 2. And so notice this condition doesn't hold. So since this does not hold, we would say that f of x is not continuous. At x equals 1. Okay, so that was the major kind of piece of limits, and limits looking at graphs and what's going on with a graph. Actually, let's go back to this. There's a lot of more questions I want you to ask about this graph. So let's look at the end behaviors of the graph. I'm gonna maybe put it over here and blow it up. I don't even remember what letter I'm on. Maybe I, J, K, J. What if we were looking at the limit as x goes to negative infinity of f of x? So we're looking at what y value x is approaching as it goes to negative infinity. If you look at this graph, as we're going to negative infinity, notice we have a horizontal asymptote here. This graph is getting closer and closer to, you can't see it too much, but this is going to get closer and closer to -1. But if it asked, what is the limit as x is approaching positive infinity? So notice here, as we're going to positive infinity, because there's an arrow here and there's no open circle or closed circle, it's continuing on this direction forever. And so as x is going to positive infinity, the graph is going to negative infinity. if you looked at what the limit as x is going to 0 on the left of f of x, so even though when a limit goes to positive or negative infinity, technically it doesn't exist, but it tells us what's going on with the graph. And so if you're looking at what's happening as you're coming in on the left of this graph has a vertical asymptote. It's getting closer and closer to this y-axis, but this graph is shooting off to positive infinity. So this goes to infinity. Okay. Okay, so that's more of what things you should know about limits graphically and algebraically. So we got into then the derivative, and we first looked at the derivative using the difference quotient and limits. So use the definition. Of the derivative. To find f prime of x, where f of x, let's say, is equal to 1 over x. Okay, so a formal definition of the derivative was with limits. And we were looking at the limit as h approaches 0, just by definition, of f of x plus h minus f of x all over h. Okay, so f of x plus h, that's telling me to take that expression, x plus h, and plug it in wherever I see an x in f of x. So I have 1 parentheses, or I'm sorry, over, I see an x here, so let's put parentheses here. And we're replacing it with this whole expression, x plus h in here, x plus h. Okay, so there's no other terms or no more x's, so I'm done with this f of x plus h piece. So then it says to subtract off what f of x is. Well, f of x, we were defined to be 1 over x. So minus 1 over x divided by h. Okay, so if we look at this and we go back in, we're going to plug in 0 wherever we see an h. But if we do that, notice in the numerator I have 1 over x minus 1 over x, which is 0. And if I plug in 0 into the denominator, I also have 0. So this was the indeterminate form again. And so that's where we had to manipulate what we were taking the limit of. So complex fractions, try getting rid of the complex fractions is usually the way to go. So I'm going to clear my complex fraction by multiplying both the numerator and denominator by the LCD of the fractions within the fraction. And my LCD, well, it's what we have over here. We have x plus h all times x. So whatever we multiply the numerator by, we have to multiply the denominator by. Okay, so if we distribute this whole piece, x plus h times x, to the first fraction in the numerator, the x plus h cancel, and you're just left with x. Minus, well, if we distribute this x plus h times x to the 1 over x. The x's cancel, and we're left with that whole piece, x plus h. We got to be careful because we have that minus sign outside. That has to be distributed to that x plus h. All over. So here, it's actually better that you don't distribute things out. So let's just leave it in factored form. And so let's leave this as hx all times x plus h. Doesn't really matter the order that you put that in. Let's simplify the numerator. I notice that when I distribute my negative, I get the limit as h goes to 0. Well, x minus x, that's going to cancel, and then I'm going to have a negative h left. All over h times x, all times x plus h, that quantity. So I notice here my h's cancel. And so we technically have the limit as h goes to 0 of a negative 1 in the numerator all over x all times x plus h. Okay, so now let's go in, and wherever we see an h, we're plugging in 0. And so we get negative 1 all over x times x plus 0. Or this is negative 1 over x squared. Okay, so our derivative was negative 1 over x squared. So show this same problem find f prime of x using a different method. Again, f of x is 1 over x. Okay, so this was not quite in the form that we could take the derivative. So we could rewrite things, and in this case, we wanted to rewrite it so that we had the x in the numerator. And so this is really x to the first power. To bring this up into the numerator, we're going to change the sign of our exponent. So this is really x to the negative 1 power. So now we can use our rules, general power rule of derivative. And so we can bring our power down front, which is negative 1, x. Now subtract 1 from our power, which is negative 2. Rewrite this so that the exponent is positive. You're just bringing down the piece with a negative exponent, so that's just the x. So you have negative 1 over x squared. Which is the same result that we got above by using the formal definition of derivative, using limits. Okay, so we looked at derivatives as being slopes and finding the slope anywhere at a particular point on a graph. We also looked at it as being the slope of a tangent line at a particular point on some graph. So this says find the equation of the tangent line. Oops. To the curve f of x equals 3x squared minus 6x plus 2 at the point, let's just say at x equals 0. Okay, so to find the equation of a line, or a tangent line in this case, we need our slope and we need a point. my point? So we can find our point by plugging this value 0 back into the original. And so if we looked at f of 0, this would equal, well, plugging in 0, that's going to get rid of the first two terms and just leave us with a constant of 2. So we have a point at 0, 2. To find the derivative, or to find the slope, we need the derivative of our function and then evaluate it at x equals 0. So taking the derivative of f of x, we get 6x minus 6. We want to set this equal to 0. So we can factor out a 6. Actually, we don't need to take this. I'm thinking of going further in math. Sorry, further in this course. We want to find the slope, so plug in 0. So we have f prime of 0. So this is equal to 6 times 0 minus 6, which is equal to negative 6. So we find our slope is negative 6, our point is 0, 2, and we want the equation of the line. So if we plug things back into y equals mx plus b, we could solve for b. So I know y is 2, so 2 equals my slope of negative 6 times x, which is 0 in this case, plus b. So I get my b value is equal to 2. So if b is 2 and my slope is negative 6, the equation of the tangent line is going to be y equals m, which is negative 6, times x, plus b, which is 2. So we found the equation of the tangent line at the x value equals 0 of f of x. Okay, so then we got into techniques of taking derivatives and different rules, the product rule, the quotient rule, the chain rule, how to take derivatives of exponentials and logs. So let's do that real quick. So if we have y is equal to, let's say 6x raised to the 4/3 power, and this is all times 3x to the 2/3 plus 1. Okay, so taking the derivative of this, I notice that if I don't manipulate this, that I would have to use my product rule. But I noticed that I can manipulate this pretty easily so that I didn't have to use the product rule by distributing that 6x to the 4/3 to each term. So here we would get y is equal to, so we're going to use rules of exponents. First, let's multiply the coefficient. 6 times 3 is 18. X raised to the, so rules of exponents, same base, multiplication, you're going to add your exponents. So 4/3 plus a 2/3 is a 6/3. Well, 6 divided by 3 is 2. So we're really just left with x squared. Plus, so distributing 6x to the 4/3 to the 1 is 6x to the 4/3. Okay, so now it looks a lot easier to find the derivative, and I don't have to use the product rule. I can just use the general power rule. So bring our power down front. This is 36. Subtract 1 from our power. So the derivative of 18x squared is 36x. Plus 6 times, bring our power down front of 4/3. X, subtract 1 from our power. So I'm going to treat our 1 as common denominator as 3/3. So 4/3 minus 3/3 gives me 1/3. I notice I can simplify this a little bit. 3 goes into 6 evenly. It goes in there 2 times. And so we find that the derivative is equal to 36x, 2 times 4, so plus 8x to the 1/3 power. So let's say you had y is equal to e raised to the 2x plus 1 power plus the natural log of the square root of x. Okay, so I could go ahead and just take the derivative right away. I could rewrite this. I'm going to need to anyways. I could rewrite that radical, the square root of x, as x to the 1/2. So let's do that. So we have y equals e raised to the 2x plus 1 power plus the natural log of x raised to the 1/2 power. So I notice that when I take the derivative right now of my natural log, I'm going to have to use the chain rule. But if I use my properties of logs, I technically could bring this 1/2, my power down front. That's equivalent. So we have y is equal to, and it would just make it easier when I take the derivative to do that. So y is equal to e to the 2x plus 1 plus this 1/2 natural log of x. Okay, so we're now in the form that we can take the derivative. So remember the derivative of e. That was nice. It was itself times the derivative of the exponent. So the derivative of the exponent, which is 2x plus 1. So the derivative of 2x is 2. Derivative of 1 is 0, so I don't need to write that, times the original e. So e raised to the 2x plus 1 power. Plus 1/2 times the derivative of the natural log of x. So derivatives of natural logs is 1 over what you were taking the natural log of, which is x, and then times the derivative of the inside, which is just 1. And so we're pretty much done. We have the derivative is 2e to the 2x plus 1 plus 1 over 2x. Okay. So given y is equal to 3x squared minus 2x plus 1, all divided by the square root of x. Okay, so there's multiple ways I see I can approach this problem. I can use the quotient rule, or because we're dividing by one term in the denominator, I also noticed that I could break that up into 3 separate fractions, use rules of exponents so that I can rewrite it where I don't have any variables in the exponent. I'm sorry, in the denominator. So it really depends. It actually might be faster just to use the quotient rule, which I think it actually is. So using the quotient rule, it's the derivative of the top first, and order matters in this case where it didn't matter for product rule. So derivative of the top, derivative of 3x squared is 6x. Derivative of negative 2x, so minus 2. Derivative of 1 is 0. So the derivative of the top, 6x minus 2 times the bottom, root x, minus the whole top, 3x squared minus 2x plus 1, times the derivative of the bottom. So derivative of square root of x, same thing as x to the 1/2 power. Bring our 1/2 power down front, subtract 1/2 from our 1/2 power, we get negative 1/2. All over this denominator, which is root x squared. Okay, so I can clean it up a little bit by distributing and combining like terms if possible. For time's sake, so I can get through more problems, I'm not going to clean that one up right now. So if it says find dy dx for the following, and we have 2xy plus 3x squared equals 4x minus 5y cubed. Okay, notice I can't get, I can't get this where it's just y equals. It says find dy dx. We want to use implicit differentiation. And so when we're taking the derivative with respect to y is a function of x, and so we had to treat that using the chain rule. So when we took the derivative of the inside, we didn't know what y was really in terms of x, we just called it y prime or dy dx. Okay, so looking at the first piece of this equation, I notice I need my product rule. And so derivative of my first piece, 2x, is just 2 times the second piece, y. That was in terms of x and not y, so I'm not going to put the dy dx. Plus the first piece, 2x, times the derivative, though, now of y. Well, the derivative of y is 1, but I took the derivative with respect to y, so this is where I put the dy dx. Plus, so the derivative of 3x squared, that gives us 6x. It was in terms of x and not y, so we're okay, equals, so derivative of the right-hand side, derivative of 4x is 4, minus, so derivative of 5y cubed, bring our power down front, we get 5 times 3 is 15, y, subtract 1 from my power, it's a y squared. I just took the derivative with respect to y, and so now I need to put on that dy dx. Okay, so we're solving for dy dx, and so that means that we want to get all the terms with dy dx on one side of the equation and all terms that do not have a dy dx on the other side of the equation. So I'm trying to group this term here with a dy dx with this term here. Anything else needs to be on the one side and all the dy dx on the other side. So let's keep the 2y and 6x on the left-hand side, and let's subtract this 4 to move it over. So if I do that, I have my 2y, I have my plus 6x, I'm subtracting a 4 to get that constant from the other side over here. And then let's also, we want to get this term with a dy dx, this 2x dy dx to the other side. So if I do that, subtracting that, I get minus 2x dy dx minus 15y squared dy dx. So now that we got all the terms with dy dx on one side, the trick is to factor that out of both of those terms. So if we factor dy dx out of the right-hand side, you're left with a negative 2x minus a 15y squared. I'm just going to rewrite the other side, bring it down. So 2y plus 6x minus 4. So now we can get dy dx by itself by dividing both sides by this negative 2x minus 15y squared. And so we get dy dx is equal to this 2y plus 6x minus 4, all divided by negative 2x minus 15y squared. Okay, so now we're looking at graphing using derivatives to help us to graph. So for the following function, let's say f of x is equal to x cubed minus 3x squared minus 9x plus 7. And so we want to use this to help us graph. And so when you're doing this to help you graph, let's find your critical numbers. So we find critical numbers by finding when our function is, finding the derivative of our function and finding out when that is equal to 0 or undefined. So looking at this, f prime of x, this is equal to derivative of x cubed is 3x squared minus the derivative of 3x squared is 6x. Derivative of 9x, so minus 9, and the derivative of 7 is 0. And so we're looking at when f prime of x is equal to 0. So I notice when I look at this equal to 0, I'm going to pull out a 3. We have a common factor of 3. So if I pull out a 3, I'm left with x squared minus 2x minus 3 all equals 0. So I also noticed that what's inside the parentheses factors, there's two numbers that multiply to -3 and add to -2. So that would be x minus 3, x plus 1. And so values that make this equal 0 would be x equals 3 and x equals -1. Oops, darn it. Okay, so critical numbers will help us with where our graph is increasing, decreasing, and it will also help us find max and mins. Okay, so find where f of x is increasing and decreasing. Oops. So we want to place our critical numbers on the number line, and we want to test intervals on the left and the right of those numbers. And so -1 is our first critical number, smallest to 3. And so we want to plug values into our first derivative and see if it's positive or negative. If we get a positive number, that's telling us our slope is positive, and so the function is increasing there. Really, we don't care what value we get, we just care if that number is positive or negative. So we could look at, if we wanted, f prime of x being in factored form, and we could just look at multiplying positive and negatives together. You could do it that way, or you could plug it into the original, it doesn't really matter. But choosing a number that is to the left of -1. So if we chose, so -2 is to the left of that. If we chose -2 and we plugged it back into the derivative, well, I have 3, which is a positive number, times -2 minus 3, which is a negative number. And -2 plus 1 is also a negative number. Multiplying a negative and a negative, that's greater than 0, and it's positive, and so we know that our function is increasing on the left of -1. So choose a number that falls in between -1 and 3 and plug it into the derivative. If 0 falls in that interval, it's always the easiest one. Plugging in 0 into the original derivative would be the easiest because that just gives me my constant, which is -9. So I know that plugging in 0, I get f prime of 0 is -9, which is less than 0, and so this is decreasing. So right away, I can see that x equals -1 is a a local max, or it could be local. It could be also, it could be in local maxes can also be absolute. We're going to need that later, so I just wanted to write it. So now choose a number to the right of 3. So how about x equals 4? So I'm going to do this as positives and negatives again. So plugging into the derivative, 4 minus 3, that's a positive number. All times 4 plus 1, which is a positive number. If we multiply two positive numbers together, we still get a positive number. And so this is increasing here. And so I can see that at x equals 3, is a local minimum. Okay, so those are not the local max and local min values. That's your y value when you plug it back into your function. And so now let's look at the intervals where it's increasing. It's increasing from -infinity to -1, union from 3 to infinity. It's decreasing between -1 and 3. Okay, so we want to find, actually I have it right here. We want to find what these so find your max and min values. So we need to plug this back into our original function. So recall our original function was f of x equals x cubed minus 3x squared minus 9x plus 7. And so if I look at f of -1, where my max occurred, plugging in -1 wherever I see an x. So I'm going to just put parentheses wherever I have an x and go back and fill it in. So I have x, so put parentheses cubed minus 3. I see an x, put parentheses squared minus 9. I see an x, put parentheses plus 7. Replacing x with a -1 and then figuring out what that value is. So -1 cubed is -1. -1 squared is +1 times the -3 in front, so -3. -9 times -1, so this would be +9 plus 7. So -1 minus 3 is -4. -4 plus 9 is 5. 5 plus 7 is 12. Okay, so we have a maximum value that occurs at -1 and is 12. I'm just going to put this down. And so our minimum value, we're looking at f of was 3. So plugging in 3 wherever you see an x. So we have 3 cubed minus 3 times 3 squared minus 9 times 3 plus 7. This gives us 27. Well, 3 squared is 9 times the -3, so that's minus 27. Those cancel. Minus 9 times 3, which again is 27, plus 7. Well, 27 minus 27 cancels. -27 plus 7 is -20. That's our min value. Oops. So that's our minimum value. Okay, so x is 3, y is -20. So you should be able to find concavity. So find where f of x is concave up and concave down. And any inflection points. Okay, so to find concavity, we look at the second derivative, and to find where inflection points occur, we're looking when the second derivative is equal to 0. Using the second derivative equal to 0, those possible inflection points, we can test values into the second derivative to see if it was positive or negative. So let's grab our first derivative. And I'm going to grab it not in factored form. Let's try that again. Okay, so our second derivative so this is equal to derivative of 3x squared is 6x minus the derivative of 6x is just 6 and the derivative of -9 is 0. So we're looking at when f double prime of x is equal to 0. So we're looking at when is 6x minus 6 equal to 0. It's a linear equation, isolate your variable. So 6x equals 6. Get x by itself, divide by 6, you get x equals 1. Notice on these, both of our times we took the derivatives, our function was defined everywhere. There was no values where it was undefined. I can't make a straight line. And so now we want to do the same thing we did as above when we were looking at critical numbers and seeing where it was increasing and decreasing. But this time we're using our second derivative. So choose a number to the left of 1 if we chose x equals 0. Plugging it into the second derivative, we want to see is that a positive or a negative number. And so if we plug in 0 into the double derivative, we get back -6. This is less than 0. So if the function double derivative is less than 0, then the function is concave down. Okay. So now choose a number to the right of 1. So if we choose 2 and we plug it back into the second derivative, I notice I get 6 times 2 is 12. 12 minus 6 is 6. And so that number is bigger than 0. So this is concave up. And so we have an inflection point if it's changing concavity, and it is changing on concavity on each side of that x equals 1. So x equals 1 is where an inflection point occurs. And so we need to figure out what that y value is. And so we need to plug that back into our original function. So if I plugged it back into my original, that was x cubed, so 1 cubed minus 3 times x squared, so 1 squared minus 9 times, I don't know what just happened. Sorry about that. Where's that? So I have -9. I was writing a parentheses. You're going to plug in 1 plus 7. So plugging in 1, we get 1 minus 3 minus 9 plus 7. So 1 minus 3 is -2. -2 minus 9 is -11. And -11 plus 7 is -4. Okay, so we know that this point is 1, -4. Okay, so putting the pieces together, you should be able to graph it. And so I would just basically, I would go plot all my max and min points and my inflection point. So we got a max at -112. We had a min at 3, -20. And we had an inflection point at 1, -4. We had it that it was increasing. Let's pull it up. Where was it increasing? Until we hit -1, and it was concave down there. So it's going to be kind of hard because I made it so skinny, but basically you're going to have a concave down graph. We can find where it's crossing the y-axis really easily. That's at 7 because plugging in 0 into the original function is my constant. So once we've hit, so it's kind of concave down, this point, it now changes to concavity as up. It's decreasing, it's hard to see it, and then goes back up. I can't, it's hard to draw. There we go. Okay. So let's look at some integration. Okay, so integration, if we had the indefinite integral of x squared all times 3x minus 4 dx. So if we wanted to integrate that, we would have to distribute that x squared inside the parentheses. And so doing that, we'd get back 3x cubed minus 4x squared dx. Okay, so when we're integrating, we're taking the antiderivative of each piece. And so the antiderivative of 3x cubed, we were adding 1 to the exponent. So adding 1 to the exponent gives us 4, and we were dividing by that new exponent. So in that case, we would have 3x to the fourth over 4. Then we have minus 4. So the antiderivative of x squared, add 1 to the exponent, which is 3, and divide by your new exponent, which is 3. This is an indefinite integral. We don't have bounds, and so this is where we had to put the plus c, plus our constant. So if we had the integral of x squared minus 4 all over x plus 2 dx. So looking at this, I'm not quite sure. I don't know how to integrate it. I would think maybe using u substitution, but then I also noticed right away that x squared minus 4 is actually factorable, and it factors to one of the factors, or the factor in the denominator, x plus 2. So let's just break that down. We can break that down. This is the same thing, difference of squares, x minus 2, x plus 2, all over x plus 2 dx. Our x plus 2's cancel, so same thing as integrating x minus 2 dx. So the antiderivative of x, add 1 to the exponent, so it's now 2, divide by our new exponent of 2, minus, so be careful here. If it helps you, if you have a constant, think of that constant. Think of 2 as 2x to the 0 power. So if you were looking at using that rule, if we add 1 to your exponent, so we have our 2 here, add 1 to our exponent, it is now 1. And divide by 1. I really don't need to show that. And so this is equal to x squared over 2 minus 2x. Oops, and I forgot my plus c plus c. Okay, so now we're looking at integrating e to the 2x plus 6 over x dx. So there's a rule that says that we could break this down, and it might just look easier if we break it down. So let's look at this. This is the same thing. We can pull that 4 out front of the integral of e to the 2x dx. Plus, so this is like a coefficient of 6 times 1x. So I can pull the 6 in front of the integral. So 6 times the integral of 1 over x dx. So if you don't have the rule for e memorized, let's just look at this using u substitution. And this is why we have that formula before. But if we had e to the 2x dx, think of it as you choose u to be the exponent, because we know that e to the u is just itself e to the u, the antiderivative. So if we let u equal 2x, we take the derivative of both sides. Derivative of u is 1 du equals the derivative of 2x is 2 dx. This is where we wanted to solve for dx and replace what we chose for u. So we could get dx by itself by dividing both sides by 2. And so dx is equal to du over 2. So you have the integral of e to the u, and dx is the same thing as du over 2. Okay, so the antiderivative of e to the u is just e to the u. This is like 1/2 in front of it. Let's see. So this is the same thing as e to the u, but u is 2x. So this is e to the 2x over 2 plus c. Okay, so there was a rule if you were looking at e raised to k times x, k being a constant. Basically, it was the original e divided by that k value. But technically, this is the work behind why you get that. And so this is the same thing as e to the 2x over 2. I'm not going to add the constant until the very end. Plus 6. So this is where you had to be careful. We had that one rule that we could, if you had the integral of x to the nth dx, which we're usually using, we add 1 to our exponent, divide by our new exponent. But there was one stipulation here that n could not equal -1. And if you look at 1 over x, if you rewrite that, this is x to the -1 power. Here, this is saying n is equals -1. So we can't do that. This was the special case. Remember when we took the derivative of natural log, we got 1 over x. Antiderivatives, derivatives undo each other. And so the antiderivative of 1 over x is the natural log of x. Now I need to add my c in here. Let's see. So notice 2 goes into 4. And so cleaning this up a little bit, we have 2e to the 2x plus 6 natural log of x plus c. Technically, you'll probably see, because of our bounds, we can't take the natural log of a negative number. This is indefinite. So maybe we need to put in absolute values here. So antiderivative x all times the square root of x squared plus 2 dx. Okay, so this case, I can't distribute that x inside of the radical, and I can't integrate it how it's written. So this is where we want to look at it and use u substitution. If we choose u to be what's underneath the radical, then we could rewrite that as u to the 1/2 power. So let u equal x squared plus 2. Take the derivative of both sides, we get du equals 2x dx. Substitute in, we have the integral of x, the square root of u, and dx we need to replace in terms of du. And du, we need to solve for dx here. So divide by 2x, we get dx equals du over 2x. Okay, so that's nice because what we chose gets rid of this x out here, and we're only in terms of u, which it needs to be. And so let's pull this. This is like a 1/2 coefficient in front. So let's put that in front of our radical. We have 1/2 times the integral of the square root of u. I'm going to rewrite as the 1/2 power, u to the 1/2 du. So 1/2 all times. So the antiderivative of u to the 1/2, add 1 to it. So 2/2 plus 1/2 is 3/2. Divided by our new exponent, 3/2. If you divide by a fraction, think of it as an invert multiplying. So just multiply by the invert or reciprocal of this. So the reciprocal of 3/2 is 2/3. And then we need our plus c. So this simplifies a little bit, those 2's cancel. And our original problem was in terms of x and not u, so we need to go back and rewrite what we had chosen u to be. We had chosen u to be x squared plus 2. So we're left with, this is a coefficient of 1/3. Parentheses replace what u is in terms of x, which is x squared plus 2, raised to the 3/2 power plus c. Because my original integrand had a radical, I would rewrite this with a radical. So the denominator is what root, so I'm taking the square root, and the numerator is what power I'm raising this to, which is cubed. So I'm going to put the 3 in the denominator, and this is the square root of x squared plus 2 quantity cubed plus c. Okay, so that gives us our antiderivative. Okay, so let's look at a definite integral. So definite integrals, those are where you had bounds on your integration. So if we were looking at the integral from 0 to 1 of 3x squared minus 2 dx. Okay, so we can take the antiderivative of each piece pretty easily. So the antiderivative of 3x squared, this is 3x cubed over 3, adding 1 to my power and dividing by my new power. Minus antiderivative of 2 is 2x. And I'm looking at evaluating this. You can kind of put a vertical bar here, kind of representing. I'm evaluating this from 0 to 1. We do not add the c when it's a definite integral. And so now we're looking at this where we're plugging in our upper bound 1, wherever we see an x. So this is the same thing as f of 1, the antiderivative of 1, minus the antiderivative evaluated at 0. So plugging in 1 wherever we see an x, well, those 3's cancel. So I have 1 cubed minus 2 times 1 minus, we need to be careful because this negative has to distribute. And if there's more than one term over here, you need to put it around the whole thing. So we have a x cubed minus 2 times 0. My x cubed was 0. So this gives me 1 cubed is 1, minus 2 times 1 is negative 2, minus, well, that's just 0. Everything cancels. And so our result, we get 1 minus 2 is negative 1. So really what that is telling me, because my result is negative, if I was thinking about this as area bounded between the curve and the x-axis, it's telling me that most of my graph, if not all of it, is below the x-axis between 0 and 1. If that's how we were interpreting the result. One more. I wanted to do one with substitution in it. So let's look at the integral from 0 to 1, x all over x squared plus 1 dx. Okay, so again, I don't know how to take the integral of this, but I notice if I let my denominator, because if this was a single term, I could break it up into multiple fractions and work with it. But since there's more than one term in the denominator, usually you're going to choose that to be your u value, or maybe something underneath the radical in the denominator. So we're going to let u be the whole denominator, x squared plus 1. So when we take the derivative of both sides, we get du equals 2x dx. We need to solve for dx, so we get dx equals du over 2x. So doing this, we have 0 to 1. Oops, but I'm going to put x equals, because I'm going to change them in a minute. I have x still in my numerator, all over my denominator, which I had chosen to be u, and dx we found to be times du over dx, 2x, sorry, over 2x. These x's cancel. And so I'm basically left with 1/2 times 1 over u. So we either need to change our bounds now or we need to change them later. If I change them now, I don't have to change my u back into x. So if I change my bounds, I'm going to let x equals 0. If you go back in here and you plug in that value, 0 squared plus 1 is 1. So when x is 0, then u has to equal 1. And so do the same thing when x equals 1. So go back in, we're going to get that 1 squared plus 1 is 2. So when x is 1, u is 2. So we technically have the integral with the bounds from 1 to 2. I'm going to pull my coefficient of 1/2 in front of my integral of 1 over u du. So this is the special case when my exponent is -1, and so the antiderivative of 1 over u is the natural log. So I have 1/2 natural log. I notice the bounds I'm putting in are positive, so I don't really need those absolute values around it. Natural log of u from 1 to 2. We change these in terms of u, so we don't have to worry, don't change this back to x. That would be wrong. So you have 1/2 natural log, plug in 2, the top bound, upper bound, minus 1/2 natural log, plug in the lower bound, which is 1. Those 2's are not going to cancel. This is basically the natural log is an exponent. I notice I can simplify natural log of 1. Remember, natural log is base e for your log. So basically this is saying e raised to what power would give you back 1? Well, e raised to the 0 power is 1. So natural log of 1 is 0. And so I'm just left with natural log of 2 all over 2. Okay, so we went through a lot of material in one class period, pretty much, I can't say everything that we covered in this class, but a majority of what we covered in this class. So hopefully that was helpful. And your final exam, I believe, is Tuesday at 10 o'clock. And so you want to take the final at the scheduled time that the final exam was in the class schedule. And if that's a problem, you need to email me and we'll set up something different. Okay. So thank you for a wonderful semester.